Hello, this is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and problems. In this video, we are going to solve a problem about the simple harmonic motion of a compound or physical pendulum.
Consider a uniform tin rod R of length 0.6 meters and mass 2 kilograms. The rod can rotate without friction in the vertical plane about the horizontal axis delta passing through its midpoint O. A particle A of mass 0.5 kilograms is fixed to one end of the rod, and the particle B of mass 2 kilograms is fixed to the other end. The moment of inertia of the rod above the axis of rotation delta is ml squared over 12. We take the gravitational acceleration as 10 meters per second squared. For small angles in radians, we will use this approximation. 1 minus cosine theta is approximately equal to theta squared over 2. Now the pendulum ABR is shifted by an angle of 0.08 radians, and then it is given an angular velocity of 0.58 radians per second. Now the pendulum is shifted in the vertical plane from its stable equilibrium position. Now this is the stable equilibrium position of the pendulum. Now let's move to the initial conditions. At t0 equals 0, the initial angular abscissa is 0 and the initial angular velocity is negative. The maximum angle described by the pendulum is less than 10 degrees. Let's move to question 1. Determine the abscissa xg equal OG equal A of the center of mass of the system relative to O. Now to determine the center of mass of the system, we need to draw an x-axis on the figure. So the origin of the x-axis is O, and it extends positively from A to B as shown in the figure. Now recall that the expression of the abscissa of the center of mass is MAXA plus MBXB plus MXO over MA plus MB plus M. Now we need to find XA, XB, and XO. Let's start with XO. XO is the abscissa of the center of mass of the rod. The center of mass of the rod coincides with the origin O of the x-axis, so XO is 0. Now, let's move to the abscissas of A and B. Now, look at the figure. The abscissa of A must be negative and the abscissa of B must be positive. Now, what are their values? A is on the end of the rod, so the distance between A and O is L over 2. Similarly, the distance between B and O is also L over 2. So that the abscissa of A is minus 0.3 because it is negative, and the abscissa of B is plus 0.3 meters because L over 2 is equal to 0.6 over 2, which is equal to 0.3 meters. Now the masses, we have the mass of A 0.5 kilograms, the mass of B 2 kilograms, and the mass of the rod 2 kilograms. And the answer is 0.1 meters. Now look at the figure. We locate the center of mass G on the figure.
Number 2. Determine the moment of inertia I of the pendulum about delta. Since the pendulum is formed by the rod, the particle A and the particle B, so I is equal to the moment of inertia of the rod plus the moment of inertia of particle A plus that of particle B. The moment of inertia of the rod is given, and it is equal to 1 over 12 ml squared. The moment of inertia of particle A is equal to the mass of particle A times the square of the distance between A and O, this distance is equal to L over 2. So the moment of inertia of A is equal to ma times L over 2 squared. Similarly, the moment of inertia of particle B is equal to the mass of particle B times the square of the distance between B and O. This distance is equal to L over 2. So the moment of inertia of B is equal to mb times L over 2 squared. Now substitute each physical quantity by its value. The mass of the rod is equal to 2 kg. The length of the rod is equal to 0.6 meter. The mass of particle A is equal to 0.5. L over 2 is equal to 0.3 and mb is equal to 2 kg. Therefore, the moment of inertia of the system about delta is equal to 0.285 kg meter squared. Question number 3. Determine the differential equation that governs the variation of theta in terms of I, A, G, T, and the total mass m of the pendulum. To determine the differential equation, we can start by writing the expression of the mechanical energy, and then we differentiate both sides with respect to time. So the mechanical energy of the system is equal to the kinetic energy of the rod plus the gravitational potential energy of the system pendulum earth. The kinetic energy is given by 1/2 I theta prime squared, where theta prime is the angular velocity of the pendulum, mgh is the gravitational potential energy of the system, m is the total mass of the system, and it is equal to the mass of A plus the mass of particle B plus that of the rod. H of G is the altitude of the center of mass of the system relative to the reference level for gravitational potential energy. The figure shows that H of G is equal to A G0, but H G or A G0 is equal to A G O G0 minus OA. O G0 is equal to A, and OA is equal to A cosine theta. Using the right angled triangle OAG, cosine theta is equal to the adjacent OA over the hypotenuse OG. So H of G can be written as A into 1 minus cosine theta. Now replace Hg by A into 1 minus cosine theta, we get the final expression of the mechanical energy, and it is equal to 1/2 I theta prime squared plus mga into 1 minus cosine theta. Using the expression of the mechanical energy derived in the previous slide, me is equal to 1/2 I theta prime squared plus mga into 1 minus cosine theta. The pendulum oscillates with small angles, so 1 minus cosine theta can be replaced by theta squared over 2. Therefore, the mechanical energy becomes 1/2 I theta prime squared plus 1/2 mga theta squared. Since friction is neglected, or the sum of the work done by the non-conservative forces is equal to 0, therefore the mechanical energy is equal constant, or it is conserved. Now differentiate both sides with respect to time. The derivative of the mechanical energy with respect to time is equal to 0 since it is constant. 1/2 I is constant, and the derivative of theta prime squared is equal to 2 theta prime theta double prime. 1/2 mga is constant, and the derivative of theta squared is 2 theta theta prime. 2 times half in each term becomes 1. Rearranged by taking theta prime as a common factor, now we have two solutions. Theta prime is equal to 0, or this term is equal to 0. But as you know, theta prime equal to 0 is rejected, because if theta prime equals 0, we have no motion. Then I theta double prime plus mga theta is equal to 0. Derive or divide both sides by I, we get the differential equation, which is theta double prime plus mga over I theta equal 0.
Let's move to part 4. The time equation of the motion is given by theta equal theta m sine omega 0 t plus phi, where theta m and phi are constants. Let's start with part 4a. Determine the expression of the constant omega 0. We will start by differentiating the expression of theta with respect to time. Now take omega 0 t plus phi as u. Remember that the derivative of sine u with respect to time is equal to u prime cosine u. So this is going to be theta prime is equal to omega 0 theta m cosine omega 0 t plus phi. Again, take omega 0 t plus phi as u. The derivative of cosine u is equal to minus u prime sine u. So this is going to be theta double prime is equal to minus omega 0 squared theta m sine omega 0 t plus phi. Now, look at theta. It is equal to theta m sine omega 0 t plus phi. And here we have theta m sine omega 0 t plus phi. So we will replace this term by theta. This is going to be minus omega 0 squared theta. Now we have the differential equation theta double prime plus mga over I times theta is equal to 0. Now replace theta double prime by minus omega 0 squared theta. This is going to be minus omega 0 squared theta plus mga over I times theta is equal to 0. Take theta as the common factor. Now, we have here two possibilities. Theta equals 0 or minus omega 0 squared plus mga over I equals 0. Now the first possibility is rejected because theta is equal to 0 only at the equilibrium position. So theta is not always 0. Let's move to the second possibility. Minus omega 0 squared plus mga over I is equal to 0, which means that omega 0 squared is equal to mga over I. Now take the square root of both sides. This is going to be omega 0 is equal to the square root of mga over I.
Focus, please. This is important.
4b. Determine the value of phi. The value of phi depends on the initial conditions, and the initial conditions are given at the beginning of this problem. At t0 equals 0, theta 0 equal to 0, and theta prime of 0 is negative. Using the time equation, theta equals theta m sine omega 0 t plus phi. Now substitute t equals 0 and theta equal theta 0, which is equal to 0. So we have a new equation. 0 equals theta m sine phi. In this equation, we have two solutions. Either theta m is equal to 0 or sine phi is equal to 0. But theta m cannot be 0. When theta m is equal to 0, we have no motion. Then sine phi is equal to 0. So phi is equal to shift sine 0, and it has two values. The first value is 0 and the second value is pi radians. One of these values represents the correct value of phi. To know which one is the correct value, we have to use this condition, theta prime of 0 negative. Theta prime is the first derivative of theta. Theta prime is equal to omega 0 theta m cosine omega 0 t plus phi. Now substitute t equal to 0 and theta prime is equal to theta prime of 0. So theta prime of 0 is equal to omega 0 theta m cosine phi. Using the initial conditions, theta prime of 0 is negative. But omega 0 is positive and theta m is positive. So omega 0 theta m is positive. Then cosine phi must be negative. Now cosine 0 is equal to 1 and cosine 0 is positive. So the value of phi, which is equal to 0, it is not an acceptable solution. Cosine pi is equal to minus 1, so phi is equal to pi is the acceptable solution of phi.
Now, let's move to part 5. Determine the value of the maximum angular abscissa theta m and the maximum angular speed theta m prime of the pendulum. We will start by calculating the value of the constant mechanical energy of the system pendulum Earth. In part 3, we determined the expression of the mechanical energy, which is 1/2 I theta prime squared plus 1/2 mga theta squared. Also, in the beginning of the question, we said that the pendulum is shifted by an angle of 0.08 radians, and then it is given an angular velocity of 0.58 radians per second. So let's replace each physical quantity by its value. I is already calculated, which is 0.285 kilograms meter squared, and theta prime in the beginning of the oscillation is 0.58 radians per second. The mass of the pendulum, which is the mass of A plus the mass of B plus the mass of the rod, is 4.5 kilograms. The gravitational acceleration is 10 meters per second squared, and the position of the center of mass A is 0.1 meters, and the angle or the angular abscess in the beginning is 0.08 radians, and the answer is 0.062 joules. Now, after determining the value of the constant mechanical energy, we are ready to determine theta m and theta m prime. Let's start with theta m. You know that when theta is equal to theta m, then theta prime is equal to 0, which means that the kinetic energy in this position is equal to 0. So the mechanical energy at the extreme position is equal to 1/2 mga theta max squared, or theta m squared. So we still have only the gravitational potential energy. Now let's replace m, g, and a by their values. So we have the mass of the whole pendulum is 4.5 kilograms, the gravitational acceleration is 10, the position of the center of mass is 0.1, and this is going to be 2.25 theta m squared. Now, to determine the value of theta m, we will apply the principle of conservation of mechanical energy. So ME, which is 0.062 joules, is equal to 2.25 theta m squared, and the answer is theta m is equal to 0.166 radians. Let's determine the maximum angular speed of the pendulum. So we have the constant value of the mechanical energy and the expression of the mechanical energy. Now at the equilibrium position, you know that theta is equal to 0 and theta prime is maximum. Now if theta is equal to 0, then GPE is equal to 0. So the mechanical energy at the equilibrium position is equal to 1/2 I theta prime m squared. Replace I by its value. I is equal to 0.285 kilograms meter squared. This is going to be 0.1425 theta prime m squared. Now, let's apply the principle of conservation of mechanical energy to determine the value of theta prime m. So, the mechanical energy at the equilibrium position is equal to 0.062 joules. So we have 0.062 is equal to 0.1425 theta prime m squared. And the answer is theta prime m is equal to 0.66 radians per second.
Number 6. In order to prevent the pendulum from oscillating, the value of A equal OG must become 0. When A becomes 0, that means the axis of rotation becomes passing to the center of mass G of the system. In this case, the pendulum cannot oscillate, it performs only rotational motion. To achieve this, the position of particle B is changed, while A remains at the end of the rod. Determine the new position of B relative to O. Using the formula that gives the position of the center of mass, OG equal A equal MA XA plus MB XB plus the mass of the rod times XO over the total mass, XA and XO are proved in the beginning of this problem. So substitute for MA equals 0.5 kilogram, XA is equal to minus 0.3 meter, MB is equal to 2 kilogram, XP to be determined, and XO is equal to 0 over the total mass. After some calculation, we get the value of XP, which is equal to 0.075 meter, and it is equivalent into 7.5 centimeter. Thank you for watching. If you like this video,
Subscribe to the channel, hit the like button and share.